clockwise and anti-clockwise. And then we have precision motor, which is also can be clockwise and anti-clockwise. So we have the press and hold 0 force to set the value to 0.
First of all, we must switch on the equipment. As we can see that there are two displays in here. And the first one is the fixed position, but we change the velocity. Okay, first of all, the first table asks about the clockwise 30 radius. So the clockwise 30 radius is you must take this radius scale until it reach the 30 radius. As we can see here, we got like a 30 radius, and we must change the velocity of the rotor motor. Also in the clockwise direction, we must change until it reach the 250. Okay, we got our 5 units. Okay, we take this scale 1.24 of the unit scale and put it into the table. And for the second, we change this into 200s. Okay, voila, we got 1.03. Okay, we do this for the 150, 100s and 50. Okay, for the second one, we must change the rotor velocity to the anti-clockwise. To change the anti-clockwise, we must hold it. For the second table, we must hold it until it use the 0 position. But this display, we don't change it. We make it still 30. Okay, we put it into the anti-clockwise until it reach the 250. Okay, as you can see here, we got this for the 250. We got this radius scale. So we must take this negative 1.05 for the anti-clockwise, and for the second one is 200s. For the 200s, we got the negative 0.81 X2. So we must continue it until the 150, 100s and 50. In case you all forgot, we must hold it still to get the null position for the display, and hold it to get this null position for this. But we also need to press and hold it. It's because it is important for the couples display.
So for experiment 1, gyroscopic operation, our aim is to prove that there is no couple unless the gyroscope has more position and rotation. Then to find the direction of gyroscopic couple with rotation to the direction of gyroscope speed and position. So for this experiment is, on the table we have rotor direction to 250 and the precision direction is 30 radian per second. rotor direction is 250 clockwise, and for the precision direction is no velocity. For our measured couple direction, we'll get 0 because there is no velocity for precision direction. So for our next experiment, our rotor direction and velocity must be clockwise with 250 radian. We only change the precision velocity from 5, 10, 15, 20, 25 and 30. So we start from 5. After we get 5, we measure the couple, which we get 0.18 Newton meter. Then we continue the experiment with 10, 15, 20, 25 and 30. Right. Based on the experiment that we have conducted, from the first experiment, if one of the rotor direction or precision direction is set with no velocity, the measured couple will be 0. Second experiment with constant precision and clockwise, as the rotor velocity increase, the measured couple increase, while the anti-clockwise, the measured couple increase as the rotor velocity increase. But from the predicted couple, the value of is negative. The predicted data was calculated using the formula. And for the next experiment, for moment of gyroscope, the rotor direction was set to clockwise with 250 rad per second velocity, and from the data on the recorded on the table, we found that when the precision velocity increase, the couple magnitude increases. The experiment will repeat, but with anti-clockwise direction, and we get a negative reading. And graph for both experiments were plotted.
Hi, I will talk about the discussion part. For the discussion, the component called gyroscopic couples are not fully complex. Depending on the size and direction of the torque arm, precision, velocity, together with the direction and magnitude of the angular velocity, the conservation of angular momentum dictates that the angular momentum of the rotating object must be maintained, since any change in the rotation axis will cause alteration in the rotation. From the data that we collect, for any inertia of gyroscope clockwise, the rotor velocity for the highest is 250 radian per s. That we got is 1.08 nm of the measured couple magnitude T. For the lowest rotor velocity, we use 50 rad over s, and we got 0.21 nm of the measured couple magnitude T. This alone shows that the couple magnitude increased proportionally to the increase of rotor velocity. The angular momentum of the rotor and the gyroscopic couple, all torque vectors G, are always identical in magnitude. This explains why the magnitude in gyroscopic coupling rises as the flywheel's angular momentum increases. There are a number of errors present in this experiment. The main one was the inability to physically obtain the required setting for the gyroscope for each procedure. To overcome this, the first run and a value around, the required value was used and recorded. This value was then used in subsequent runs. It varies over each, but it always keeps close as physically possible. Okay, we come to a conclusion. In a conclusion, a gyroscopic pair can only be created if a gyroscope has both a flywheel rotation and a precision rotation.
If only one of these characteristics is present, no gyroscopic couple will form. The couple will become in the direction of the flywheel leading edge. A gyroscopic couple magnitude will rise proportionally as precision velocity and rotor velocity rise.